All right. So, like was just mentioned, probably all of you have heard of ensembling before, and it's kind of a, something that doesn't invoke like newness. It's not deep learning, So it's something that I have a particular interest in, and hopefully I will get you guys excited about it today. So, so the theme of the talk is how to ensemble at scale, and so one of the things that people, I guess, necessarily think of when they think of ensembling is it takes a long time to do. You're training a lot of algorithms. So how do we do that on big data, and how do we do that fast is kind of the idea here. So just who I am. So I work as a statistician and machine learning scientist at a company called H2O AI. We have a booth outside, which you may have seen. There's a lot of yellow at it. So we're in Mountain View, California, and what we do is we produce open source distributed machine learning software. And I have a background in biostatistics and computing, and I've worked at a couple of different startups, and what I like to do most is develop open source machine learning software. Okay, so this is the overview. So I'll give a little introduction and try to motivate you guys to get excited about ensembles the way that I am. And then I'll go over what's called stacking, and also sometimes called super learning. And that's sort of the most common type of, I'm not going to say the most common type of ensemble learning, but the sort of the baseline for all of the other work that I'm going to talk about is stacking, and so then all these other things that follow that will be different variants of stacking, and using subsets, using online learners, and all sorts of things like that. And then I'll talk about each of the different software projects that I've worked on in these areas. Okay, so motivation. I guess this is sort of more in the introduction category, but the two types of ensembles that people are most familiar with are bagging and boosting. So random forest is the sort of canonical example of bagging, and GBMs, or gradient boosting machines, is the other popular boosting algorithm. And so sometimes I see on the internet, I see a blog post saying like the definitive guide to ensembling in R, Python, and there's just no mention of anything other than like random forests and boosting, and it makes me sad, because there's this whole other area of ensembles that fall into the category of stacking that I think are much more powerful. Certainly as an individual algorithm, random forest and GBM are quite popular, but why stop there when you can get more performance, assuming that's something that you care about. So stacking is the idea of taking multiple algorithms. Maybe they're different algorithms, maybe a random forest, a GBM, an SVM, a GLM, maybe even a deep neural net. And then you actually use machine learning to learn how to combine them together. So I think one of the common misconceptions about stacking is that you basically just say 0.3 times random forest plus 0.2 times GBM equals whatever. And so there's this idea that you just come up with these sort of coefficients magically. So if you're on Kaggle, or if you've used Kaggle before, there's a lot of stacking, but it's a lot of it is just people kind of just guessing numbers and things like that. So, which can also still work better than a single algorithm sometimes, but that's not what stacking is. So stacking actually uses a process called metalearning, which is taking I guess any other algorithm. Usually it's something like GLM or non-negative least squares, or even deep learning as a metalearning algorithm, and I'll talk about that a little bit more. Okay, so I'm still trying to motivate here. So some of the strengths, I can't even read my own slides, I guess. I should, oh, they're there, okay. Okay, let me just go over here. Okay, so I didn't memorize all the reasons, I guess. So some of the strengths are, basically they work better than everything else. So that's one big strength. And that's pretty much it. So they get better performance, and if that's what you care about, then you should be thinking about ensembles. But then you also have to think about the weaknesses. So why are people not using these all the time? I guess when I first heard about stacking, I thought, well, I don't understand why isn't everyone using this for every single algorithm, like that they're training all the time, what gives? I thought it was some sort of conspiracy or scandal. So, so the reason is, number one, it takes a lot longer to train if you're training multiple models and you're not doing that in parallel. So another reason, so we've heard a lot today about like sort of looking into models and making them interpretable. So this is kind of the exact opposite of doing that. You're just adding complexity. And then, if you have big data, it's even more difficult because you have to train a lot of models on a lot of big data. And then the other, what I think is the main reason is that there's not good software to do this. And so that's what I spent a lot of my PhD doing, is writing software to make this more easy, because I was using tools that someone else had written to do this stuff, and it was just, I really had a goal that I wanted to be done with a PhD in 4 years, and that was just never going to happen if I was using this software. So I would wait for weeks, really, and sharing resources on a university cluster, and it was just taking forever. That was sort of like before I discovered Amazon EC2. So so maybe it's a little bit easier now. So okay, so what is stacking, and what is this term superlearning, and where did that come from? Because that's another, I'll use that term a lot, and so I think it's good to sort of talk about where this came from. So, so the first sort of invention of stacking was by a guy named David Wolpert, and he wrote a paper in 1992 called Stack Generalization. And he's kind of the inventor, I guess, of stacking. And what he did was blend neural networks. And he was a computer scientist, so he had a lot of maybe different terminology that he used when he described things in this paper. So it might have been why it took a few more years for the statisticians to figure out what was going on. So then Leo Breiman wrote a paper. So Leo Breiman is the inventor of random forest, among other things, and he got into stacking as well because, of course, he likes ensembles. It kind of makes sense. So in 1996, he wrote a paper called Stacked Regressions, and he sort of modified the version of Wolpert stacking into what it is now, where you use cross-validation within the algorithm to generate what's called level 1 data, which I'll explain on the next slide. So he also didn't do a whole lot of blending different types of algorithms together, although he was aware that would be something some people might like to do, so he wrote about that. And so before 2007, there wasn't any theory about why this worked. It was kind of like a black box, and people understood that it worked and were using it quite a bit, but nobody knew why it worked. So that's where in 2007 there was a paper called Superlearner, and it actually first started out as a bunch of theory just about cross-validation, and then so this person, Mark Vanderland, was my advisor at Berkeley, and so he wrote this paper and sort of by accident proved how stacking worked, and then actually didn't even realize it was stacking at first and called it superlearning. So, so that's where the term superlearning or superlearner comes from. So that's kind of a term that if you hear that word, it means the exact same thing. So, and it actually took me a while to realize that as well. And I was like, oh my gosh. Okay, so anyway, so then the first R implementation of this superlearner was in 2010, so not that long ago. And that's called the superlearner package. And there's also, before that, in the software Weka, there was a stacking function. But that's basically it up until 2010. Okay, so this is the superlearner algorithm. This is kind of like what I think of when I think about it. It's like all these different fighters or whatever, and they all have their own powers, but like individually they all have weaknesses. So if we bring them together, it's this wonderful thing. Okay, so the superlearner algorithm is actually quite simple. If you understand what cross-validation is, you pretty much know everything that you need to know already. So, so this is the beginning of any sort of supervised machine learning problem where you have an X, which is your design matrix, and a response column Y. And in stacking terminology, we call that the level 0 data. And then what you need to do is specify a bunch of learners for your ensemble. Let's say there's L of them. So when I say learners, I mean learners with all the model parameters as well. And then you specify a metalearner, which you can just think of as another machine learning algorithm. And then the first step of the superlearner algorithm is to perform k-fold cross-validation on each of the learners, and basically then collect the cross-validated predicted values that you get out of that. And so what that looks like is you have, for each of the L learners, you have this new column of cross-validated predicted values that you've gotten out of doing the k-fold cross-validation. And what you do is you stack them. I don't know if that's really where the term stacking came from, but to me it kind of makes sense. So you column bind them or C bind them together so that you get this new matrix called Z. And Z is just made up. It's just a letter that's used, but basically this is your level 1 data. So in this new matrix here, it's made up of the predictions from the base learners. So there's L columns and there's N rows, just like you started with your training data. And so then you can just use your original response vector Y as the response for this learning problem. And now you can just do train another algorithm using Z as your input data. So this is called the level 1 data. And so what you do is this is the metalearner. And so what the metalearner does is it takes the output from the base learners and combines it together in some way and then produces a prediction for Y. So that is the superlearner algorithm. So it's pretty simple. Okay, so the issue was that the superlearner R package was the only thing that I had access to, and it was it worked really well, but only on small data. So so now we care about big data. So I came up with some ideas about how to extend this. So a couple different ways is you can actually change the superlearner algorithm itself and into something else, and other options are use a better language than R. That would be a first step. So C++, Java, Scala, whatever. Or then the third option is use online learning algorithms so that you don't have to think about memory and stuff like that. So these are all different approaches. And so here's 3 different versions of this that I created. So Subsemble is actually just an R package, and it implements what's called the Subsemble Algorithm, and I'll explain what that is. It's basically just a version of the superlearner algorithm that operates on subsets. Then there's something called online superlearner, which was implemented using VW. So VW, Vopal Wabbit, is a library for online learning, and it's very fast. And so basically that was an obvious choice for getting us a bunch of learners that I could use. So one of the difficulties in designing software for stacking is just getting some software that has a bunch of algorithms in it using a common interface. So there's actually not that many things like that. So there's maybe scikit-learn in Python, or the Caret package, or MLR package in R. And then the H2O Ensemble is the third approach, which uses the H2O. So similar to scikit-learn and some of these general machine learning packages, H2O is sort of a distributed, scalable version of that. And so that was why I chose H2O to implement a superlearner on as well. So I should probably go quickly through this. So Subsemble is basically what it does is you take your original data set and you partition it in. Actually, I'm going to skip this slide and just show you the picture. So this is your original data set. So let's say these are rows and columns. Actually, those are not columns. Think of each of the things that look like columns there as your whole data set. And there's 5, sort of column things, and that each one of those represents an iteration in your 5-fold cross-validation. So what you're going to do in Subsemble is instead of training on the full data set, you want to train on littler problems. So the idea with Subsemble is to squish your machine learning problem into the size that fits on whatever hardware that you have. So if if your data is so big that you can't really learn on all of it at once because of certain hardware limitations that you have, you should be able to sort of like mush your problem into an appropriate size, and that's the idea here. So in this case, I've divided the data set into 3 partitions. So there's 3. The first one's sort of highlighted in yellow, and then the second 2 are just the other 2 partitions. So for the first, if you look at on the left here, what's this say? I don't know if this is a pointer, but on the very left, what you see is in yellow, that's your training data for that iteration. And your test data, or your validation data on that iteration, is the blue pieces there. So what you do is you train on like the piece of the subset, but then you validate on the held out piece in the subset, and then the matching held out pieces in all the subsets. So when you do that, you actually are able to get predictions for the full data set again. So your training actually happens on little data sets, but your testing happens on big data sets, and then you can basically save on RAM that way. So so it's essentially doing the same thing. So instead of, in the superlearner algorithm, we ended up with level 1 data that was n rows by L learners. And then for Subsemble, you end up with n rows by J times L. So J subsets and L learners is the size of your level 1 data. And then you just proceed the same as superlearners. So this is just like an idea of, with the number of subsets, like how the performance increases in terms of time. So superlearner is the red one there, and Subsemble with 2 subsets is the middle, Subsemble with 10 subsets. So you can kind of just smash it down into whatever size you need. And it helps if the number of parallel processes that you have, or parallel training tasks that you have, is smaller than or equal to the number of cores that you have available, because then you can just do it all at once. Okay, so the idea with Subsemble is squeeze it into a bunch of little parts. Since I'm running out of time, I'm just going to go a little bit fast. And I posted these slides on my Twitter, which is just my last name, LeDell, so you can look more closely at them later. Okay, so online superlearner is the same idea as superlearner, except for you just use online learners as your base learners. And this was more of like an experiment. I had to sort of hack VW to get this to work instead of using it as a library as it's intended. And so it kind of all, like, there was some updates made, and then it all kind of fell apart. And so I didn't feel like rewriting it. But there is a tagged version on GitHub that still works. So anyway, the idea is instead of using learners that you require being trained in batch mode and loading all the data into memory at once, you can just iterate over each of the learners all at once. So you train them all incrementally, and then you update the Z matrix or the level 1 data also incrementally, and then there's different parameters where you can keep a certain amount of that data around, and then you train your meta learner incrementally as well. So that's way too fast to understand that, but there's more details in my dissertation. And then lastly is the H2O Ensemble. This is just a little bit more about H2O. So if you are familiar with Trevor Hasty, Rob Tibshirani, or Stephen Boyd, those are our academic advisors at H2O. So we work with them to try to implement some of their new algorithms as well, including one by Stephen Boyd that's pretty cool lately called GLRM, Generalized Low Rank Models, which is new. Okay, so distributed machine learning, basically it's just an implementation of the superlearner algorithm using distributed machine learning algorithms as the base learners and the meta learner, and so everything gets done very quickly. And to scale it, you just add cores, is kind of the idea behind H2O. It's meant for commodity hardware, so it's just, the idea is that commodity hardware at least is cheap. CPUs on Amazon are cheap, so you just add, and then it scales. And so this is just an example of how it would scale. So the blue is just a single workstation. This is actually a very old chart, but cluster, it's actually been entirely rewritten since I made this chart, but this is what I what I had. So cluster of 96 cores, and then the red one below is 320. So there's where you can learn a little bit more, and there's my contact information, and thank you very much.